And hopefully, we're going to hopefully have recording for people that are not here today. From the two. This way. Okay, so your turn. Any problems?
Number 16 on homework 10.
Okay, problem number 16, homework 10. Let's see. Okay. So this is, let's see. Well, you have a person, his weight is 605 newtons in this portion. So what should be his mass? Should be about a little bit less than 60 kilograms. Steps on a spring, scale in the bathroom. The spring compresses by this distance. What is the spring constant? So this is a typical question about finding the spring constant. So you have here is the bathroom scale, attach spring to it, and when there is no person on the scale, the end of the spring is here. So this is your 0 point. So introduce a coordinate system that is this way. Let's say the 0 point here, x-axis, or whatever axis you want to call it. But now with the person on top of that scale, you have compressed the spring by a distance equal to 0.67 centimeters. You have to convert that into meters. So this is distance x, displacement from equilibrium position. So they want the spring constant in newtons per meter. Therefore, you have to convert the distance x into meters. And look how it works. You have, when the person is on top of the scale is at equilibrium. So the forces that act in downward direction, and the only force is mg, has to be cancelled exactly by the spring force F. And the spring force F in magnitude, the directions are shown. The spring force F in magnitude is equal to the spring constant multiplied by the displacement. This is Hooke's law. This is the general, this is what the entire chapter 10 is based on, Hooke's law. And that's it. So this equilibrium position means that F should be equal to mg. In other words, spring constant times x should be equal to mg. And therefore, the spring constant should be mg divided by x. mg is, for my version, it is 605. For your version, mg is going to be some different number. So this is a very basic question. Usually, if I write a question like this on the practice test or the next midterm, it is going to be a multiple choice just because of the simplicity. But if it is not multiple choice, I may ask you to draw the diagram. So this is part A. Part B, what is the weight of another person that compresses the spring by different distance? So if the difference, well, you do exactly the same thing, but you already know the spring constant. So for part B, you just say k times the different displacement x prime should be equal to mg prime, let's say, right? So the spring constant is already known. The different displacement is given. What is mg? Well, multiply those and you get mg is your answer. And multiply the spring constant that you just found by the new displacement x prime in meters again, and it should give you the answer. Okay, questions? Okay, if no questions, let's see some other problem maybe. Anybody?
Could you do number 18 on homework 10?
The same problem?
Yes, and more.
18. Okay, so this is another simple problem, but it requires understanding of what is going on. So let me write the equations that we have from chapter 10. Well, at least the most important equations look like this. Hooke's law, negative k times x. Hooke's law is what generates oscillations. After that, we have using this analogy, this correspondence between the motion of the projection of a rotating object and the oscillating object, we found that the position as a function of time changes as a cosine function. Cosine of omega t. The velocity of this oscillating object changes as negative a times omega times sine of omega t. Acceleration as a function of time is negative amplitude times omega squared times cosine of omega t. The angular frequency omega, we demonstrated, is equal to square root of k divided by m. The angular frequency is 2 pi divided by the period of oscillations. And the angular frequency also can be written as 2 pi, the frequency f, because f is the inverse of period.
I have a
So,
question real quick.
yeah.
For period of oscillation, what does that mean?
The time interval between two successive, the time period for one complete oscillation.
Okay.
So going forward and coming back before it starts going again, you have completed one period.
Okay.
Right? It is important. So, for example, let's get strings here. It is important to realize what definitions means. So this is oscillating back and forth, back and forth. If I start the clock from this position, the most to my right, so one period is going to be the reading of the clock when this comes, goes back. This is one period. And after that, the motion repeats itself, so it is a second period after that, and so on. But this period is exactly this time interval. Now, they give you here, in this problem, this is an important problem because it tries to invite you to make sense of those formulas that are on the board.
So would you say it's important enough to put on a test?
If you remind me before I write the test, so when I announce the date of the test, which is going to happen after we complete four chapters, chapter 9, 10, 11, 12. When I complete those 4 chapters, and I'll say, okay, what time do you want the test, the midterm test? And we make a decision together. And I usually write the tests of the day and sometimes of the night before the test. But you have email, you can always send me an email and say, oh, you promised to give some problem of this type. And if I give a problem like this, it may not be exactly this diagram, but it is going to be something very similar, not so that you to be able to read diagrams. It is a useful skill. So you have an object with given mass. So this is problem 18, right? You have you have given mass. The spring harmonic motion displacement as a function of time is showing. With the aid of this data, determine first the amplitude of the motion. Well, you read the amplitude. Here is the amplitude. It is 0.08 meters. You just read. Part B, angular frequency. Well, look, frequency is the inverse of the period. The period is here, the period is this number of seconds. This time interval is the period. So you say the period, for my version, the period is 4 seconds. Therefore, the frequency is 1 divided by period. It is 1 divided by 4 seconds or hertz, which is 0.25 hertz. And angular frequency omega is 2 pi the frequency. So from a diagram like this, the easiest thing to read immediately is the period. And this is what I did. From the period, I find the inverse, which is frequency. And once you have frequency, multiply it by 2 pi if you want. And this is your angular frequency. Okay, now, spring constant. How to find the spring constant? This is part C. How to find the spring constant? Well, here's the spring constant. You have omega, you have the mass. What is the spring constant? So you can say, since omega is square root of k divided by m, it follows that omega squared is equal to k divided by m, from which it follows that k is equal to omega squared multiplied by m. Right? That's the spring constant.
And is M mass?
M is the mass, of course, yeah. And what is the speed of the object at 1 second? Here. 1 second happens to be exactly the time when you have the maximum displacement. So at time 1 second, maximum displacement means that the cosine was equal to 1, right? This is, which means that omega t at that moment of time is equal to, let's say, 0, or, well, it is not 0, but it is, well, let's leave it as cosine to be equal to 1. let me see if I can figure it out in a simpler way. Yeah, you can look. What is the speed of the object at that moment of time? If you look at the slope of the curve around this maximum, the slope is positive here and negative on the other side of the 1 second moment. The slope is exactly the velocity. So the velocity is positive here, negative here. What is going to be in the middle? It goes to 0. Right? This is one way to argue. If you know trigonometry, you can argue geometrically, but this argument that I gave you is foolproof because not everybody knows trigonometry. So again, velocity of the object is the slope of this curve. The slope is positive here, negative here. Therefore, exactly in the middle, it is 0. Velocity is 0. Exactly at 1 second mark. And speed is magnitude of velocity. So speed is 0. The next part E. Part E says find the acceleration at 1 second. So look, at 1 second, displacement is at its maximum value, the amplitude. Therefore, the cosine of omega t is 1. And if you look at the acceleration at that moment of time, this is 1. And therefore, the acceleration is going to be at that moment of time, t equal to 1 second. At that moment of time, the acceleration is going to be negative. The amplitude is 0.08 meters multiplied by omega squared, which is the number that you already found. Omega squared, which is the number that you already found. They're asking for magnitude, so forget about the negative algebraic sign.
Could you explain why cosine omega t is 1 again? I kind of missed that.
So the cosine and sine function, their maximum value is 1. And well, here you see that the displacement has maximum value. So the maximum value occurs when the cosine is 1.
Okay.
So that's again, trigonometry is not a required course, but it should be. A little bit of trigonometry, at least some experience with sine and cosine functions. People that see them for the first time or they have forgotten how to work with trigonometric functions have much harder time. I realize that, but this is the name of the game. Okay, other questions about this problem? If not, other problems, your choice.
How did you find the negative 0.08 again?
I substituted here. So I have that acceleration as a function of time is negative a times omega squared times cosine of omega t. And I figured out that at time t equal to 1 second, the cosine gives you is exactly as the value of 1. So I have amplitude times omega squared. The amplitude I read from the diagram, right? This is the maximum displacement. Omega squared is what is in the formula here for acceleration. And I don't write the cosine because the cosine is equal to 1. The minus sign is also in the
I
formula.
see that.
Minus sign is also in the formula, but since they ask for magnitude, no negative numbers, no negative magnitudes cannot be negative. Other questions? Okay, let's see other problems then. Your choice.
Can you do 21 on the same one?
So I didn't talk about pendula in class. I'm going to do it tomorrow. But we can write the result right here. And the result looks like this. It's problem number 21. We're going to demonstrate that the period of a pendulum is 2 pi square root of L divided by the acceleration due to gravity, G, 9.8. This is something that we have to demonstrate. We have to prove that, I think. I hope that I have that formula right. Let's see. Yeah, something like this should be the case. So knowing this, so they say that you have a simple pendulum. They give you the length of the simple pendulum, L. For me, it is 0.78 meters. Oh, they give the mass. Huh. You don't need the mass to find the period, but okay, they give the mass of the pendulum. You pull it away from equilibrium position at some angle and release it. Assume that no friction and the motion is simple harmonic, angular frequency. Motion. Okay. So we can answer part A immediately without taking into account that they give mass and displacement. So they're asking what is the angular frequency omega. And omega is 2 pi divided by the period. In other words, it is 2 pi divided by 2 pi square root of L divided by G. 2 pi cancels out. The inverse of square root of LG is square root of GL. And this should be the answer. 9.8 divided by the length under square root. Determine the total mechanical energy of the pendulum as it swings back and forth. Look, you have to do some geometry again here. So remember this formula for the period, and let's look at the diagram. So here is the vertical axis. Here is the pendulum at its maximum displacement, angle 9.2 degree. So this angle theta given. Here is the mass attached to it. So basically the pendulum is going to go along this circular path back and forth. Right? So we know this length L of the string of the pendulum. So they say using the position at the lowest point, yeah, okay. So look, here is the lowest point position. This is your 0 for a coordinate system, let's say that points up. Well, X, Y, whatever you want to call it. Y-axis, let's say. So this is the 0 of your y-axis. What is this height right here? So if you draw this height, this is going to be 90 degrees. What is going to be this height, this distance? Well, if you look at the large right triangle, from here to here, from here to here, this side is going to be L times cosine of theta. Is this side right here. And therefore, this part only is going to be what is left if you subtract from L times cosine theta. So this is the height, call that height H, let's say. That height is H, and this is its value. H is that. And well, look, in algebra, you always have to write the things in a way that is more, well, I don't know, it's not shorter, but it is more neat. And look, this is the maximum displacement of this mass. At this position, so when the pendulum goes back and forth, at this position, the speed of the pendulum is 0. Right? At that position, for 1 instant, it doesn't move. 0 speed means no kinetic energy. The only energy that this object has is gravitational potential energy. So the energy, the gravitational potential energy at that position is mgh. In other words, it is mg L1 minus cosine of the angle that they give you. This should be the answer for the energy of the object. So that energy stays unchanged, but it is transferred between gravitational potential energy at the very top, 0 gravitational potential energy when the object passes through this position, but all that energy is converted into kinetic energy, 1/2 mv squared when it goes to the lowest point that has height 0. And so this is your reasoning for part B. And for part C, they're asking, what is the speed of the object when it goes through this point? Well, at this point, we said all of that energy is transformed into kinetic energy. So you have kinetic energy is mv squared at that particular point. And that kinetic energy is equal numerically to mgl times 1 minus cosine. Right. This is the height. And from here, canceling the mass, you get v squared is equal to 2gl 1 minus cosine of theta. And therefore, the speed is square root of this expression. So v is square root of 2gl 1 minus cosine of theta, everything from the squared. Right? This should be it. So here is the answer for part B, and this is the answer for part C. And the answer for part A was this.
Can you explain again how, for the height, you got L minus L cosine theta?
This is the height, right? But the same height is right here if I read this triangle up. This side of the triangle is L times cosine. So this length is going to be whatever is the length of the string minus you subtract this part, right? This is the total. From the total, you subtract this part and you're left with this, which is the height. You have to draw this diagram independently because, well, this problem and probably some other problems are solved doing this construction. The trajectory of the pendulum. Other questions?
So. Alright, so L is the length of
Of the string,
the
yeah.
string.
So it goes like this. So this is L, this is L. It's the radius of this circular arc. Okay, other questions? Okay, let's see other problems then. So, by the way, for the next midterm, the most important chapter is chapter 9, the previous chapter, and chapter 10 is almost the same level of importance. Chapter 11 is a different game, fluids. So Archimedes principle, buoyancy, and chapter 12, I think, is the first chapter from kinetic theory of gases. Well, all material is important, but probably the more challenging material is chapter 9 and chapter 10. Okay, other problems?
Can you go over 18 for? Or not 18, sorry, 17?
17?
Yeah.
Oh, this one requires drawing. So you have, okay, let's see how to handle problem number 17. And actually problem number 17 is, let's see. Yeah, that's going to be, okay, let's see. Somebody already asked me to solve this problem. Was it in class or it was not in class? Okay. Because it looks familiar, which 17. So you have uniform stick with given length suspended from two springs with different spring constant. So here is, so two different springs, imagine they're very different. And here is the stick that is attached like this. Then They give you the string constants, the length of the string, the mass of the rod. And they say that even though the two springs have different spring constants, their original length, unstrained length, is the same. Find the angle between this stick and the horizontal. In other words, find this angle. Here it is. So hopefully like this, find this angle. Oh. Let's see how it should work. So here is the first spring. Here is the second one. Which one is a larger spring constant? 63, 37, very different spring constants, which means that this one is going to stretch further. So this is the original length of each spring. So they are attached at the same level. So this is your 0 point, 0 of the coordinate system. I'll put the coordinate system in a minute. So choose the coordinate system with positive axis this way, positive x-axis this way, but this is the 0 point. And after that, this one is going to stretch. This one is going to stretch more. X-axis. So, and as a result of this different stretches, your rod is going to look like this. And they want us to find this angle. Angle theta.
Do
They
you
want-
think you could explain like what spring constant means or like what it's representing?
It is defined here, but it represents how stiff is the spring. Larger spring constant means that it is more difficult to stretch it. So, but the definition is here.
Yeah.
The coefficient of proportionality between the force that the springs generate once it is stretched at a distance x from its equilibrium length, from its equilibrium position. So let's say this first spring constant is K1, the second spring constant is K2. So for me, K1 is 63 newtons per meter. Right, this is 63. This is, since it is larger than K2, it stretches less. The spring is more difficult to stretch because it has larger spring constant. And now this means that the distance this stretched is distance x1, right? This distance. And the distance the other stretched from here to here is the distance x2 for the second spring. So this problem is good because you have to now not only draw the setup, but now you have to put together the free body diagram, showing all the forces that act on this stick, together with the location where those forces are applied. So you have, I'll put this as arrow only in one direction because it is displacement. But this is the first spring applies a force F1. Right? And this is the spring force. The spring applies it to the rod. That spring force obeys hook flow. And the second spring is going to apply a force at this end, a force F2. Again, another hook flow force. And the only other force that acts on the stick is the weight. And that weight acts at the center of mass, at the center of gravity of the stick, which is right in the middle. So you have that the length of the stick is, so this length is L. And this length is L. And in this position, the stick is at equilibrium. The condition for equilibrium is the net force acting on the stick to be zero. So let's see what is the net force. Well, you have mg in positive direction in my coordinate system. You have F1 in negative direction, F2 also in negative direction in this coordinate system, right? I selected positive direction to be down. It doesn't matter where you select it, but once you select it, you have to stick to that. So, well, this is good equation, but let's write it in terms of what is given. F1 is a spring force, F2 is a spring force. Therefore, their magnitudes are going to be given with Hooke's law. So you're going to write this as mg minus k1 times the displacement of this end, x1. And the other one is going to be k2 times the displacement x2 equal to 0. So this is the condition which says that the net force acting on the stick has to be 0. But this is not sufficient. The stick also must be subject to 0 torque, 0 net torque, so that it doesn't rotate. Well, the torque is always with respect to some axis of rotation, but you can choose the axis of rotation of the stick anywhere you want because the stick is not rotating. So I would choose the axis of rotation of the stick to be right in the middle where the gravity force acts. And this is going to make the torque generated by gravity 0. So I'm just going to have the torque generated by the force F1 and the torque generated by force F2 as non-zero torques. So choose, I actually can choose other axes of rotation, but let's choose it in the middle to have certain symmetry and the things to look nice. Okay, let's write first the torque generated by force F2. By definition, torque is of a force is equal to the magnitude of the force, which is F2. Later on, I'll write it as K times X, but for the moment, let's make it clear. Multiplied by the lever arm of that force with respect to whatever axis of rotation I have chosen. Lever arm is the distance between the axis, the line of action, and the axis of rotation. So the distance between this point and this dashed line. Well, that distance is right here. Call that distance L1. L2 because it belongs to force. It belongs to force F2. So F2 times L2 is the torque. And that torque is positive. It wants to rotate the stick in counterclockwise direction. And by convention, this type of force has to have positive torque. Okay, the torque of gravity we said is 0 because the lever arm of gravity is 0. After that, I need the torque of the force F1. So here is the line of action of the force F1. The lever arm is the distance between the axis of rotation and the line of action. That distance is right here. So in other words, this is distance L1. And the force F1 wants to rotate in clockwise direction. So by definition, such a torque has to be negative. Negative F1 times L1. This is the net torque, and the net torque must be equal to 0. Well, let's rewrite this last equation by taking into account that each of the forces is a spring force. So F2 is K2 times X2. So K2 times X2 times L2 minus K1 times X1 times L1 equal to 0. Now let's see. L1 and L2 are equal. You can see that by noticing that, well, this triangle is equal to this triangle. So L1 is equal to L2, and when you divide both sides of this equation to L1, which is equal to L2, this cancels out, and this equation looks like this: K2 X2 minus K1 X1 is equal to 0. So I divide both sides of this equation to L1 and take into account that L1 and L2 are the same number, and it disappears. Okay, so now I have to clean a little bit of real estate. But if you asked for some problem, so where can I clean some space? Let's start maybe here. So the two equations that are left are this one and this one. So the first equation reads mg is equal, so I'll move the two terms to the other side of the equation with opposite sign, k1 x1 plus k2 x2. And the second one reads the second one is going to read what? Okay, the second one is going to read, I'll write it like this: 0 is equal to k1 x1 to k2 x2 minus k1 x1. And I just copy this, but first write the 0 maybe. Does it matter which name? Okay. So I have two equations with two unknowns, x1 and x2. From those two equations, I can find the unknowns, x1 and x2. How? Well, if you add those two equations together, the left-hand side is going to read mg, and the right-hand side, this and this go away because they have opposite signs, and you're going to have 2 times k2 x2, right? And therefore, you can say x2 is equal to mg divided by 2 times k2. Here's one length that I just determined. K2, x2 is this length that I just determined how long this distance is. Once I have this distance, I can substitute in one of the other equations and find x1. So for example, I can take this equation and write it like this: k1 x1 is equal to k2 x2. Therefore, x1 is k2 x2 divided by k1. But I already have x2, so I can substitute x2 here. I'm going to have k2. Instead of x2, I'll write it's equal mg. Well, okay, mg divided by 2 times k2, and all of this divided by k1. So let's see what's going to come out of this. So k2 here and k2 cancels out. So this x1 happens to be exactly mg divided by 2 times k1. It is pretty much the same expression like this. So here is x1, here is x2. In other words, I just found this one, and I know this one. And now look at the triangle that is formed. Look at this triangle. It is a right triangle, which the angle that I'm looking for is in this triangle. And well, can you tell me what is the length of this side? The length of this side is this minus this, right? This minus this gives me exactly the length of this side of the triangle.
When you're drawing the free body diagram, how did you like where did x2 come from? Like that certain amount of length?
It is some unknown amount of length, but I just calculated its value.
No, but like when you're drawing it, how do you like know where you're? I'm just confused on how you drew it, the free body diagram, like the x2 and the x1, like how you knew where to put them.
Well, I could have drawn them in a completely different manner. It is just some distance that I don't know. I didn't know when I was drawing that distance, but I calculated it later on. So, well, so here is the setup of our problem. Here are the 2 springs. And here is the stick that is attached. So when I attach the string, the stick, both of them expanded, but the stronger spring expanded less than the other. So I didn't know by how much each spring expanded, but I drew some distance, and later on I found this distance numerically. So I really didn't know where is x1 and where is x2. It is some distance, arbitrary distance. You draw, but you know that in this situation, the stick is at equilibrium, doesn't move in any direction, doesn't rotate in any direction. Right? So in science, you draw the diagram, and after that, the lengths are determined by the numbers that are given. But in this case, they are not determined explicitly. You just calculate that. And we just did this calculation. I don't know if I answered, but if somebody has a better answer, please speak up.
Practice. All practice.
Well, if you go over this problem, you're going to have a very good understanding of chapter 9 and relatively good understanding of chapter 10. Even though it is a problem from chapter 10, it is practically chapter 9 torque and equilibrium condition. Okay, so that's it. So I have to erase the board to finish this. So you have this hopefully, right? So erasing this part right here. And looking at the triangle, I formed a right triangle, and with the angle that I'm looking for is at this triangle. So this length of the triangle, of the side of the triangle, is exactly x2 minus x1. Right? Because x2 is this, x1 is this. When you subtract, you get exactly this length of the side.
Would it not be forced to? Or is that not?
Say it again?
Could it be, is it not equal to forced to?
No. So again, the lengths of the force vector are arbitrary
Okay.
lengths that I just draw some force vectors, but they're not equal. The length. So this is x2 minus x1. This the hypotenuse of the triangle is the length of the stick L, and I can say x2 minus x1, that length, divided by the hypotenuse, by definition, is exactly sine of the angle theta. The definition for sine is opposite to the angle side divided by hypotenuse. And therefore, the angle theta is equal to inverse sine of x2 minus x1 divided by L. And you can do some arithmetic and hopefully, yeah, you can do some arithmetic and bring this expression into simpler form that you can enter in. You can enter in your calculator. So x2 is mg divided by 2 times k2. x1 is mg divided by 2 times k1. Like this. In other words, you can factor out the mg, and you're going to get some, well, so you're going to get that theta is equal to arc sine. So how can you simplify this? Well, just leave it like this. I can, on the side, I can simplify it, but I don't want to make it too. On the side, I can simplify it. So I can, okay, so let's do, let me calculate on the side somewhere. Well, leave it like this. This should work. But if you feel comfortable to add and subtract and divide fractions, you can simplify it yourself. I can do it somewhere, maybe right here. So x2 minus x1 was equal to mg divided by 2 times k2 minus mg divided by 2 times k1. So this is equal to mg divided by 2, and in brackets you have 1 over k2 minus 1 over k1, and therefore the angle is going to be, theta is going to be arc sine of mg divided by 2 times L multiplied by 1 over k2 minus 1 over k1, and this, put more brackets. This should be it. Yeah, this is probably the easiest way to simplify it. Right. Want to simplify it further? No, it's no, that's the simplest. Okay, so it is a long problem, but again, if you understand it, if you are able to do it first with a little bit of looking at your notes, and after that without looking at your notes, you should do very well on the next midterm, because this is chapter 9, which is the more difficult chapter. Well, and a little bit chapter 10. And actually, I can provide incentive. If you show me your work, meaning that first write it by looking, after that write it independently, just looking at the problem without looking at the solution, or the logic, write it well, and I'll give you extra credit for the next midterm.
For this problem.
For this problem, yeah. If you want, I can put it in the midterm. But you shouldn't just memorize the answer. So by the way, check the answer, because I may have made some mistake somewhere, but well, who knows, maybe. I cannot recover even if there is a mistake, I cannot find it because most of the solution is erased. But it is a good opportunity to get some extra credit for. If you want, if everybody agrees, or at least most of the class agrees, to have this problem on all versions of the test, I can put it on all versions of the test. Just think about it and let me know.
Thank you.
Why did you? You had it like set equal to 0, and then you changed it to, well, you got rid of mass times gravity, and then you brought it back.
Did I write? Did I? Let me see.
Don't know.
Let me see.
So
Yeah,
this is the
okay.
sum of the forces. right?
Yes, this went. Yeah, and so I wrote this on the other side of the equation, right? MG, what is it? Well,
Do I
keep
not
it
have
this way.
Okay.
And after that, the other one is this. And this. So the system of equations is this minus mine, and this is okay. Okay, so well, people, we actually exceeded 1 hour.
Mhm.
So let me write what was the so the first equation reads like this: mg is equal to k1 x1 plus k2 x2. Do you see it from your notes?
Mhm.
Just okay. And the second equation reads 0 is equal to k2 x2 minus k1 x1.
Mhm.
So this is the original system that eventually we solved. Do you see those two equations in your notes, or you don't?
I do. I have them both in my notes.
Okay, and the rest is solving those two equations together as a system and determining x1 and x2. And you can do it in different ways, but if you add the two equations, if you add them, you're going to get mg is equal to 2 times k2 x2.
Right.
That's it. And therefore, you get x2 is equal to mg divided by 2 times k2. Right, here it is.
Mhm.
And after that, substitute that in one of the other equations. So substitute it here. And you're going to get, right, this thing to the other side with opposite sign. X2, K2, X2, X1 is this, substitute, and you get K2 mg divided by 2, right? And you get this.
So, I don't know.
No, do it slowly, do it slowly.
Well, I mean, I understand that part of it. I guess I don't understand how we went from talking about the sum of the forces to,
Some of the torques.
oh,
The net torque also is 0, right? So this second condition here is from the torques. I canceled the lever arms because they were equal. But the torque of the first force, the torque of the second force is negative. They have to add it to 0. The gravity has 0 torque. I didn't even write it.
gravity has 0.
So the weight, the lever arm of the gravity force is 0 because I took the axis of rotation to be in the middle. So the lever arm of this,
Oh,
it just not.
okay, okay.
Okay, so go ahead if you have questions about this one.
No, that was where my missing link was.
Okay. Should we leave other problems if you have other problems for tomorrow, or we can do them now?
I'm good now.
About you.
I'm good.
Okay, so let's stop the recording. This is the end of the recitation session.